Hello everyone, welcome back to online discussion recordings for CS184. Today we're going to be going over probability in Monte Carlo estimators. So let's go ahead and get started. So first up, there's some short terminology, some introduction. So some of this you'll have already seen in the math intro, but we can just briefly go over it again. So expectation is the probability weighted average of all possible values. So in the discrete case, it's that first equation. In the continuous case, it's the second one. Basically, just an integral replaces the summation. The variance is the expected value of the squared deviation from the mean. So it's the expected value of x minus the expected value of x squared. And it basically is a measure of how far the values of this random variable are from the mean. Okay. The cumulative distribution function, most often called the CDF, is the probability that a sample from distribution x will take on a value less than or equal to some specific value x. And then last, this one is new, Lagrange multipliers. And so it's basically a method to find the maximum or minimum of a function f of x subject to some constraint g of x is equal to 0. And so we create this new function, capital L, which is equal to f of x plus lambda times g of x. And then we look for the critical points where the gradient of L is 0. And that those points are the maximum or minimum of f. Okay? So let's go ahead and get started. First up, we're going to work on the inversion method. So if you recall the inversion method, basically, if we have a uniform random variable u in the interval 0 to 1, we can generate a random variable from any other one-dimensional distribution if we have access to the inverse of its cumulative distribution function, right? And so the reason is the cumulative distribution function f of x is going to take a value anywhere in the range of this random variable and return a number from 0 to 1. So what we want to do is take the inverse, which is going to take a number from 0 to 1 and then give us some value corresponding to that number in the domain of the random variable. So if we can basically randomly generate samples between 0 and 1, we can randomly generate samples of any random variable. Okay, so let's go ahead and see. And so we use this to choose sample points when running ray tracing. And so let's go ahead and do an example of this on this for problem number 1. Okay, so what function of u will return a sample from the exponential distribution with parameter lambda? This distribution has density p of x is equal to lambda e to the negative lambda x. Okay, so let's go ahead and get started. The first step is to find f of x, right? So it's going to be f of x is equal to, remember, the way you get the CDF is by integrating, so 0 to x of lambda e to the negative lambda x dx. If we write this out, this is going to be, so we're going to I'm just going to go ahead and take the antiderivative. It's going to be negative e to the negative lambda x from x to 0, right? So that's going to be negative e to the negative lambda x minus negative 1, right? Because anything to 0 is 1. And so that's going to be equal to 1 minus e to the negative lambda x. Okay, so that is f of x. That is the CDF of the exponential distribution. Now the next step, now that we have this, is we want to invert it, right? We want to find the inverse of f of x. So we can do this by, there's a classic method where you switch x and y and then solve. So we can go y is equal to, so actually let me go ahead and just switch it now. X is equal to 1 minus e to the negative lambda y, right? So it's going to become, actually, e to the negative lambda y is equal to 1 minus x, right? Take the log of both sides. So then we're going to get negative lambda y is equal to log of 1 minus x. And here, the log is the natural log. Okay, that's kind of just implied. And then the last step, we get y is equal to okay, so there it is. That's the inverse, right? So this is equal to f inverse of x. And so basically what this is originally this f of x took a value in the domain and gave something between 0 and 1. F inverse of x takes something between 0 and 1, gives you a value in the domain. So if we have a random variable u between 0 and 1, and we want to get a sample, all we would do is, let me come up here, it would just be negative log of 1 minus u over lambda. Okay, so that is our answer. It's an example of the inversion method. We started by taking the PDF. We found the CDF by integrating. Once we had that, we inverted it, and then we basically just replaced x with u, and that's how we got our answer. Okay? So this is something that'll come up again in this class, so it's some good practice. Okay, next up, we're going to look at rejection sampling. So rejection sampling is one way of using the Monte Carlo method to sample from a probability distribution. So we repeatedly sample values from a proposed distribution and then accept or reject based on whether it falls within a certain range or PDF that we know to sample from. So if we sample falls outside, we reject. Inside, it does. And then, that's how it works. So what we're going to do in this problem is we're going to use rejection sampling to estimate pi, right? And so the method A generates random points uniformly in an equilateral triangle. So that's this triangle right here. And method B does the same thing, but uniformly in the square. Okay, so both of them estimate pi using the ratio of the number of points within the circle to the number of points total. Okay, so let's do this. First of all, we're going to look at the triangle. So how is this going to work? Suppose k out of all n points sampled that lie within the triangle circle, then a formula for the estimated value of pi is. Okay, so let's write this. So what we can write is we can write a ratio between k and n, so k over n, and the areas of the circle and the triangle. Okay, so the area of the circle is pi r squared. Obviously, r is the radius of the triangle. And then the area of the triangle, now this is a little tricky, but if you look it up, the area of an equilateral triangle with an inscribed circle of radius r is 3 root 3 r squared. Okay, so quite simply, we can cancel the r squared and then do some manipulation. So we can move pi over to the other side, or actually we can just multiply both sides by 3 root 3. And so here, I'm just going to move down a little. And then so we can get pi is equal to 3 root 3 k over n. Okay, pretty simple. We basically just set up this ratio of total points to the areas because we're sampling uniformly, we can do that. We can assume that the number of points hitting it is proportional to the area, and then we just solved for pi, and there we go. Okay, so now we're going to move on to number 2, and in number 2 what we're going to do is the same thing, except instead of the triangle we're going to use the square setup this time. Okay, so let's do the same thing. So k over n is equal to pi r squared. This time, if you look at this, the side of the square is 2r, right? Twice the radius. So the area is going to be 4r squared. Once again, r squareds go away. We rewrite this and we get pi is equal to 4k over n. Okay, so there we go. That's our estimator based on the square. Very similar setup to the triangle. It's just a matter of the area of a square is different than the area of a triangle. Okay, so let's keep going. Now, number 3. Which method, A or B, has lower variance with the same number of samples? Okay, and so the way we can do this is look at this and say, well, if we look at these drawings, when we sample from B, the square, a larger number of points are going to end up within the circle, right? Because there's less of this kind of white region around it, as opposed to this triangle, which has significantly more. And so basically, because a larger percent of these points will land within the shaded area, B will have a lower variance. Okay, so there we go. B will have a lower variance because of the area. More points will fall within the shaded area, which is what we're interested in. Okay, So now let's look at this. What are some downsides to using uniform random sampling? So remember, uniform means every point equally likely to hit, right? And so the biggest downside is because it's equally likely to hit, it's possible that, we might need to get a lot of samples. So it's possible that what happens is, we're hitting this and we go here, 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 all these points before finally getting one here, which, this wouldn't help us much. We would probably have a very bad representation of pi if we were to use, these samples I just drew. So the downside of uniform sampling is we might get a lot of samples that don't really help us answer the question. And so it just might take, a lot more before we finally get a good number. Okay, so some downsides might take a lot of samples. Okay, and so often we kind of try to get around this by importance sampling, which is we kind of sample where we think it's more important. And so, we'll see more of that coming up. Okay, number 5 now. So what are some downsides to using rejection sampling for high dimensional spaces? Okay, and so one of the downsides, and the biggest downside, is that when we use this for high dimensional spaces, we often run into a problem called the curse of dimensionality, which means because it's a high dimensional space, we're going to have a lot more samples rejected than accepted. And so this essentially becomes a very similar problem to the uniform random sampling, where we would have to take a lot of samples before we're able to get a good estimate. So in high dimensional spaces, the efficiency of rejection sampling goes way down. Okay, so it's less efficient, needs more samples. Okay, so that's the downsides to using rejection sampling for high dimensional spaces. It's not as efficient, and we need a lot of samples. Okay, so let's keep going. So the next problem is about unbiased Monte Carlo estimators. So the Monte Carlo method can also be used to estimate an integral. In the last problem, we were using it to estimate a value. When this method is used properly, the expectation of an unbiased Monte Carlo estimator is equal to the true value of the integral. So that's the definition of an unbiased estimator, is that the expectation of the estimator is equal to the actual value you're trying to estimate. Okay, so let's look at the first problem. You have two random variables, x and y, which are drawn uniformly from -2 to 2. Okay, so what is an unbiased Monte Carlo estimator for the given integral? All right, so the general kind of setup for an unbiased estimator, Monte Carlo estimator, and the hint says your answer should include a summation over n samples, is going to look something like this. Okay, it's going to be 1 over n, we sample n times, and then it's going to be f of xy over p of xy. Okay, where p is the probability of getting this specific sample. And the reason is basically, if we were to take the expectation of this, if I would put, expectation, remember this linearity of expectation means we can put the expectation inside. So it's going to become 1 over n times, the summation n of the expectation of f of x comma y over p of x comma y, right? And so that is going to be equal to, now see, because we're summing up n of the exact same thing, this 1 over n and the summation of n are going to cancel out, right? And so we're basically just going to get this expectation of f of x comma y over p of x comma y, which, if you remember, is equal to the integral over all xy, integral over x, integral over y, of the value inside the expectation times the probability, right? That's the definition we saw right here, right? expectation of x is integral of x times the probability of it. So if we come back down here, we have this cancels out with this, and we just get this integral, right? Which is exactly what we were trying to estimate. See right here, that's what we're basically trying to estimate. Okay, so we're going to want to follow this exact setup. This is kind of the setup we want to follow right here, this 1 over n and then the summation. So let me kind of separate this off. And then let's get into the specifics of this particular problem, right? So we can set up the same thing. You know, our estimator is going to look 1 over n, summation over n, right? And here I'll put I equals, 1 to n, and then f of x I comma y I over p of x I comma y I, right? And so now, in this problem specifically, what we can do is actually get a value for this p of xi, yi, right? And the reason is we know that x and y are both drawn uniformly from -2 to 2, okay? So for any, so if I come up here, p of xi, yi is equal to p of xi times p of yi, right? Because they're both independent, they're independently drawn. And if I write this out, the probability of it being any value in this range of 4 is just 1 over 4, right? For x and for y. So it's going to be 1/4 times 1/4. And so that's equal to 1/16, okay? And I'm sorry, I'm doing this in such a messy way. But, okay, so now we have a value, a numerical value for p of xi, yi. And so we can come back here. We can go equals 1 over n times the same summation, I goes from 1 to n, of f of xi, yi over 1 over 16, right? Because that's what we just solved for. And so then if we just simplify, we'll get 16 over n times the summation from I equals 1 to n of f of xi, yi. Okay? And so there we go. That is our unbiased estimator. I suggest, take the expected value, make sure it comes out to what we expect it to come out to. And so that's our unbiased estimator, okay? So once again, just following this general kind of layout setup where we have this summation over n, average it out because we're taking n samples. So you got to somehow kind of bring it back down to 1. And then the p of xy in the denominator, because when we do take the expectation, we're going to multiply it by p of xy, and those two will cancel each other out, and we'll get the integral that we want. Okay? So that's an unbiased Monte Carlo estimator. These will definitely come up most likely on the exam, so good thing to know. Okay, let's keep going. So next up, we have the minimum variance estimator. So suppose we're trying to integrate a function f on some domain. So in this case, it's I is equal to this integral of f of x over dx, right? And so we have this typical Monte Carlo estimator, looks just like what we did last time, except in this case, it's just a single sample. So there's no summation and no 1 over n. And then, so if we take the expectation of this estimator, we same integral multiplied by p of x, the p of x's cancel, and we get the integral we want. So this is a basic form of importance sampling. And if we then calculate the variance, right, which is the expected value of f of x over p of x squared minus the expected value squared, is this equation right here. And if you solve it out, we get this. It's the integral of f of x squared over px minus I squared, where I is this integral, the actual integral we're trying to calculate, okay? So as we saw in question 2, estimators with lower variance are desirable because it means we get a better estimate after taking less samples. So it's more efficient, faster, it's just better in every way, right? So let's try and find an estimator that minimizes this variance, okay? And so to do that, we'll use Lagrange multipliers, which we introduced at the beginning. So in order to solve for the minimum variance sampling distribution P, we would have to use the calculus of variation. So there's the Lagrange multipliers. But we can solve the discrete case using Lagrange multipliers. So in this case, we have a discrete function f of I and a probability mass function p of I. And so what we want to find is, what is the discrete distribution p of I that solves this? So minimum, we want to minimize this over all p of I, the sum of f of I squared over p of I, subject to this constraint that the sum of p of i's is equal to 1. Okay, so what we're going to do is we're going to follow that Lagrange setup. So we're going to get L is equal to, remember, it's f of x plus lambda times the constraint, right? So in this case, it's going to be this sum over I of f of I squared over pi, that's our f of x, plus lambda times our constraint, which in this case is going to be I is equal to 1 to n p of I minus 1. Okay, and the reason we do this minus 1 is because if I come all the way back up here, you'll see this equation works because the constraint is g of x is equal to 0. So by subtracting that 1, we're basically just saying that this whole thing inside the parentheses is equal to 0. Okay? So then what we're going to do is we're going to take the derivative of this. So the derivative with respect to p of I, okay, so then we're going to get dp of I, and it's a partial derivative because it's L is a function of multiple things. It's f and p. Okay, anyway, so what we're going to get is negative f of I squared over p of I squared plus lambda. Okay, so that's the partial derivative. And then we're going to keep going. So now what we want to do is set this equal to 0, right? So if we set this equal to 0, we can solve for p of I, right? And so if we go ahead and solve it, we move, the lambda to the other side, divide the minus signs will go away, f of I will come over, take the square root, and what we're going to get is p of I is equal to absolute value of f of I over square root of lambda. Okay, so this is it. P of I is equal to this equation, right? When we set the partial derivative to 0. So now what's the next step? Well, we were given this constraint that the sum from I equals 1 to n of p of I is equal to 1. So let's put that constraint to action, right? So let's come over here. We'll say sum of I is equal to 1 to n of f of I over square root of lambda is equal to 1. Okay? And so then what we can do is we can do some solving. We can do the square root of lambda from the bottom can just come out because it's not, it doesn't depend on I. And so once that comes out, we can move it to the other side. And what we're going to get is the square root of lambda is equal to the summation from I is equal to 1 to n of f of I, right? And so if we look at this, what we're going to see is now we can plug this equation back in here, and we'll get p of I is equal to absolute value of f of I over the sum overall, let's make it j, because, I is already used in this case, of f of j. Okay, so we were able to find, so remember, we're looking for the distribution p of I, right, that makes this the case. And so we found an equation for this p of I, but the issue is that this p of I is dependent, or it's actually proportional to the f, the function f that we are trying to sample from, right? That's the discrete function. And so in this case, we can't find p without knowing f, but that's exactly what we're trying to find. Okay, so in this case, it's the best choice for p, the minimum variance choice for p depends on the function you're trying to sample, or the function you're trying to find. And so, so the function you're trying to find, and so we can't find an exact answer. Okay, that's basically the takeaway here, is that the best minimum variance estimator depends on the function we're talking about. Okay, so there's that. Not really an answer, but kind of an answer. Okay, let's keep going. So number 6, multiple importance sampling. Okay, so in the previous question, we showed that the optimal estimator is the distribution f of x itself. In many cases, right, and so actually, if that wasn't clear, I guess I didn't really make that clear. So look, f of I is some value of I, right? It's a discrete, the function, it's a discrete function f, which has all these possibilities from I equals 1 to n. And so the probability of any one value I is f of I over the sum of all f's, right? That's the probability. And so basically the minimum variance estimator depends on the function, right? It is the probability function, and that's why we can't get an answer. So hopefully that makes it a little more clear. So coming back here, that's what we found in the previous question, and in many cases, we don't know what that ideal distribution f of x is. So one solution is to combine the strengths of multiple different sampling distributions. This technique is called multiple importance sampling and can result in a pretty robust and low variance estimator. Okay, so with that in mind, suppose we have two different sampling methods, P1 and P2 for I. Remember, I is this integral that we want to calculate. Samples from either of them can provide an estimate for I, right? We can set up an unbiased estimator and find an estimate of I. But we're not sure which one is better. Is P1, P2, which one has lower variance? And what we might want to do is put them both together, ideally combine their strengths, and then hopefully get something that's better than either one alone. Okay? But the key is when we combine them, we want to make sure that we're still have an unbiased estimator. Okay, that's most important, because if we don't have an unbiased estimator, then what we're doing doesn't really matter. We need an unbiased estimator. Okay, so number 1, what constraint on the two constants W1 and W2 will make the following estimator unbiased? Okay, so let's just write this down. Let's take the expected value of this. So the expected value of W1 times f of x1 p of x1 plus W2 f of x2 p1 of x2 is equal to, okay, wow, I really did not leave myself a lot of space, but nonetheless, that's fine. So remember, properties of expectation. These w's are constant, so we can pull them out. We can distribute the expectation to each of these individual terms. And remember, as we did up top, the expectation of f of xi, p of xi is going to be I, right? It's an unbiased estimator by itself. So what we're going to get is, let me just write it here. So it's going to become W1I plus W2I, right? Because the W1s come out, expectation of these fractions is I. And so what do we want this to be? We want this to equal I, right? So here, where should I write this? Give me one second. Sorry, guys. Okay, let me come over here. Come over here. We want W1I plus W2I is equal to 1. Equal to I. And so, hopefully this is pretty simple from here. We just can divide out the i's and we get that the constraint we want to put on this is that W1 plus W2 is equal to 1. Okay? And that makes a little bit of intuitive sense too. We want the total, the two constants to sum up to 1. And so that's what we need for this estimator to stay unbiased. Okay? Okay, cool. So let's keep going. Sorry, I was messy there. Similarly, what is a sufficient constraint on the two functions w1 of x and w2 of x for the following estimator to be unbiased? Okay, so now it's a slightly different case than before, because before we had constants w1, w2, and now we have functions w1, w2. Okay, so we're going to do the same thing. Here's what I'm going to do. I'm going to save myself some space and just put the expectation here. Right, it's equal to, now, we can't pull the W1, W2 out anymore because it's a function, right? So what we're going to do is split this up into two integrals. W1 of x, f of x1, p1 of x1, sorry, that's the next one, plus another integral, W2 of x2, f of x2 over p2 of x2, right? Then we can come over here. Remember that, oh, whoops, I actually made a mistake. So let me do this. Let me take this, move this there, and so this is, right, we have to multiply by this. Right, then these cancel out, and we get integral of w1 x1 times f of x1 plus w2 x2 times f of x2. And there should be dx's. I'm sorry, I'm kind of omitting those, but, and then remember we can put these two together because they're integrals over the same domain, right? The domain of x doesn't change. And so we can do that and factor out this f. So it's going to become f of x times w1x plus w2x dx. And we want this to equal I. And if we come up here, all the way up here, I is equal to just the integral of f of x. So what we want is, once again, we want this whole term to drop out, and the way we do that is saying w1x plus w2 of x should equal 1. Okay, so kind of a similar constraint to what we saw in the constant land in the function land. And so that's what we need to do to keep this estimator unbiased. Okay, so that's all for this discussion. Next time we'll be talking about a little bit of camera lenses and maybe some materials. So